Here we have 1/6 power of 2i over 1 plus I. And what this is asking is really, it's looking for a complex number whose 6th power is equal to 2i over 1 plus I. Well, that's because if you had z as denoted as the 1/6 power, then if you take the 6th power both sides, then 6 and 1/6 multiply to cancel each other, and you end up with this z to the 6th equals to 2i over 1 plus I. Now keep in mind that if you have a 6th root question, z to some 6th power equal to this number on the complex plane, in the real case you only look for one positive answer. Here on the complex plane you have 6 different answers. If this 6 was like 10, then you would end up with z to the 10th power equals to 2i over 1 plus I, and that would be 10 different answers. Okay, now one key to compute such a thing is to represent the given number in polar form, r angle theta, which is a shorthand for r times some cosine angle theta plus I times sine angle theta. Okay, now because you want z to the 6th power written in polar form, we're not going to do the usual division, where if you divide two numbers you're supposed to do like multiply the conjugate of the denominator top and bottom. I'm not going to do that. Instead, I'm going to make both top and bottom by polar form. And if you have both top and bottom by polar form, you can easily do the division by doing the following. You divide the magnitudes, but the angles subtract. And this is true because of this Euler identity, right? This is same thing as r1 e to the I times theta 1, and r2 angle theta 2 would be r2 angle e to the I theta 2. So the Euler identity tells us that when you actually do the division, this is the same as r1 over r2 and e to the I theta 1 over e to the I theta 2, but if you have the same base, the exponents subtract, right? So the end result is that you have r1 over r2 equals to e to the I theta 1 minus theta 2. And that's why, since if you rewrite this using the Euler identity backwards, you get r1 over r2 angle of theta 1 minus theta 2. So that you can think of this as like a proof of why this is true. Okay, so now what is 2i then? 2i is on the complex plane. It's 2 steps in the imaginary direction. And therefore, since it's 2 steps away from the origin, the r value is 2, whereas the angle is 90 degrees from the positive real axis, so it's 2 angle 90 degrees, okay? So 2i is equal to 2 angle 90 degrees. What about 1 plus I? 1 plus I will be 1 here, and then I here, and you have this. And because of the symmetry, this is like cutting right as a diagonal, exactly halfway. So this angle would be 45 degrees. And using the Pythagorean theorem, square root of this length is 1 and that length is 1, so 1 squared plus 1 squared, that gives you square root of 2 as your length. Okay, so therefore r value is radical 2, and the angle from the positive real part is 45 degrees. Okay, so therefore 2i divided by 1 plus I would equal to 2 angle 90 degrees and radical 2 angle 45 degrees. Now 2 is square root of 2 times square root of 2, right? And therefore if you divide by square root of 2, one of them will cancel. And the angles, we just mentioned that they subtract. 90 degrees minus 45 degrees will be 45 degrees. So that's what this right side is equal to, okay? which means what we want to solve is, I want to know for which angle its sixth power is equal to square root of 2 angle 45 degrees. Okay. Now, then after you make this number into the polar form, you should always do that. You should always make the number to a polar form. Then you rewrite z as r angle theta, because then we can make use of the fact that r to the sixth power is z to the sixth power is the magnitude get the same exponent, but this number gets multiplied to the angle, and this is called the de Moivre's theorem. And therefore I can replace the left side as r to the sixth power angle 6 theta equals to radical 2 angle 45 degrees. And now let's see what this is saying. Therefore r to the sixth must equal to radical 2, which means r must be square root of 2 1/6 power, and because square root of 2 is 1/2 power, this is 2 to the 1/2 power to the 1/6 power, which is 2 to the 1/12 power. Okay, so you have r equals to 2 to the 1/12 power. What about angle theta? Well, angle theta, 6 theta, should equal to the 45 degrees, right? So you can say it's equal to 45 degrees. But wait, we're looking for 6 different answers here because that's 6, right? If you have r value as this one value, and if you solve this for theta, you get one r value and one angle, so you're going to end up with just one answer. So what's going on? Well, it turns out that because this angle theta is between 0 degrees to 360 degrees, if you take the sixth multiplication, it will be between 6 times 360 degrees and 0 degrees. Okay, so you have more than the full circle. See, a circle is 360 degrees, but it can go beyond. Now, why does this make any difference? Well, you need these two numbers, this polar form and these two polar forms, to agree. Now, when do two different polar forms give you the same answer? Well, because polar forms represent a number by a length and an angle, you could hypothetically go beyond 360 degrees and get some angle that's beyond 360 degrees. For example, 360 degrees plus 45, which is 405 degrees, would be actually the same landing spot as the 45 degree one, meaning that these two, 45 degrees and 405, are what's called the coterminal angles. So 405 is coterminal with the 45 degree angle. Alright? And you can make more until you get to 6 times 360. So what you can do is you can do 360 plus 45, 360 times 2 plus 45 degrees, and all the way up till 360 times 5 plus 45 degrees. And 5 times 360 is the maximum you can go, because if you do 6, then it will be beyond 360 times 6, the maximum allowed angle. Okay, so you can divide by 6. Now 45 divided by 6, if you use a calculator or something, you're going to find that it's 7.5 degrees. And 360 divided by 6 is 60. 60 plus 7.5 will be 67.5 degrees. The next one will be 60 times 2, 120, and then 7.5 degrees. 60 times 3 is 180, and then 7.5 degrees. 60 times 4 is 240, and then 7.5 degrees. And then finally, 60 times 5. If you divide this by 3, if you divide 360 times 5 by 6, you get 60 times 5, which is 300. And then 45 divided by 7 would be 45 divided by 3 will be 7.5. So these are the angles, and therefore the answers would be that you have 2 to the 1 over 12 power angle 7.5 degrees, 2 to the angle 2 to the 1 over 12 angle 67.5 degrees, all the way up till 2 to the 1 over 12 angle 307.5 degrees. Okay, so these are the answers, and since I don't want to put all of these into the calculator, in your calculator we use the fact that this identity that I talked about. See, you can use this formula to find the rectangular form. If you know the polar form, you can use this formula to convert to rectangular form. And because the original question was written in rectangular form, you have to write all your answers in rectangular form. So that means I have to plug in, to convert this, we have to do 2 to the 1 over 12 times cosine of 7.5 degrees plus 2 to the 1 over 12 times cosine, no, sine 7.5 degrees, and so on and so on. Well, this will have times I, and so on and so on. But that's too much work, so I just made some Python programs to calculate it. So let me show you what I have. This is called Python language. I imported, well, you don't have to know this, but it's pretty cool to know it because it simplifies stuff, okay? So you import the NumPy. I define the sine cosine functions again because the NumPy package only has sines with radians. So this converts a degree into radians and uses the NumPy sine and cosine functions to figure it out. And I made this special function which changes the r and theta into x and y, the formula that I just discussed. The r cosine theta and r sine theta gives you the real and imaginary parts in rectangular form. And then I made the list of all the degrees as I wrote, and I just used the for loop, printed out, and these are actually the answers. And I actually used the preprint here. Oh, actually I want to change this a little bit. I want it to be a plus bi, where the a comma b is the unpacking of these numbers, the real and imaginary parts. But sometimes I saw these plus minuses, as you see it right here. I don't like that, so I'm going to replace that with just a minus. Okay, let's hope that this works. Okay, great, it worked. So these are the answers. Perfect. I'll just copy them over here, and that's it. This last bit you really have to take patience and use your calculator, or you can just look up my code and see if you can do that on your Python program. That'll be even nicer because you can learn Python from it. Alright,